Hello, welcome everybody. This is the ninth live session of Points of Topology NPTEL NOC course. This is the ninth session. My name is Shobik and working on Costume and Madras. So this is the ninth live session for this course. So officially uh, there are three sessions left, but as per request, I will take one more extra session. So that means there are total four sessions still left, and last session will be of 1 hour. Okay, so that's the thing. So before starting further, please let me know whether I am audible and the screen visible properly. Please let me know. Please let me know whether I am audible and is the screen visible properly. Please let me know whether I am audible and is the screen visible properly. Well, just hold a moment, please. Well, can you please confirm whether am I audible and is the screen visible properly? Okay, so since there is no response, so I'm assuming that everything is working fine. Okay, so before starting further, please let me know whether I'm okay. Before starting further, I hope every audio or video things are clear, so there is no issue. Okay, before going further, please let me know whether there is any kind of doubt or questions from the previous session or from assignment. Any kind of doubt or questions, please let me know. Please let me know whether there are any kind of doubts or questions. Please let me know whether do you have any question or doubt from previous session or last sessions. Okay, so in case you have any questions, so please unmute yourself and let me know. So for the time being, let me start by solving some introductory problems for Kumarishan. Okay, so so what we have done in the last session? In the last session, we have gone through compactness. Okay, so in the last session, we have gone through compactness, and today's we shall solve few problems for compactness. Okay. So before that, there are few properties we need to use. We have done those properties in the last class. If you wish, you may go through it. Okay. But the thing is that, however, so there are a few properties of compactness in the matrix as well, because the compactness matrix is very interesting. Okay. So now let me write down those properties. So let XD be a matrix space. Then following are equivalent. X compact option 2. X is complete and totally bounded. Just hold a moment, please. Well, so either x is complete and totally bounded, so this is one, and second is x is compact totally bounded. Option 3 is every infinite set has cluster point. Option 4, every sequence has a convergent subsequence. Every sequence has a convergent subsequence. Okay, these are the total 4 options which we these are for 4 properties which are interesting in case of metric space. Okay, so second property stays, so third property is that infinite has a cluster point, and fourth property is every sequence a convergence of sequence. Okay, so using these properties various problems can be solved. Okay, okay, so before that there is some interesting functions we need to use. So there is a function called distance function. So let x naught belongs to x. Sorry, the function is that let sorry let a is the subspace of x. Define a function dax is equal to infimum of all of dax a belongs to a. So that is we will have found dA is a function from where to where, x to r, x going to dx. This function is uniformly continuous. You can check this in your home, so there is nothing to do. Okay, hmm. So this can be done by, you can do it by yours. So there is nothing to explain actually. So that means now, so prove that dx equal to 0 if and only if x belongs to a closure. Okay, so the hint is that use definition of infimum. Okay, please please try to solve it. Mustaq, please try to solve it. dx if and x belongs to a closure. Please try to solve this by yourself. Okay, please take your time.
Can I repeat this question?
Yes, sure, Mustaq. So this question tells that, so there is a, so that means, so this question tells that we have a, so we denote a subset a sub of x, and then we denote the distance function. Okay, now the point is that dx equal to 0 if and only if x belongs to a closure. That's what you need to prove. So please take your time and try to prove this. And the hint is that you have to use the definition of superinferior from basic real analysis, so there is nothing complicated to use. Are you able to figure this out? Any idea, any guess? Any idea, any guess how to approach this? Okay, so the argument is as follows. So there are both directions we need to solve, right? So suppose dx equal to 0. That is by definition what? Infimum of dAx. A belongs to A equal to 0. Okay. So choose an epsilon greater than 0. Sorry, choose 1 by n. Okay. So by definition, there exists an such that 0 less than dan comma x less than 1 by n. Okay. So now consider the sequence in A. Okay. So this particular equation gives that the that the sequence n converges to x, and the sequence n and a is sequence in A. So this implies what? X belongs to a closure. So that's what the argument is. So that means what? Hold on. What? Hold on. What? There is something wrong with this. So the argument, this tells what? That whenever dx equal to 0, it implies x belongs to a closure. Now conversely, assume x belongs to a closure. Okay. We need to show what? Dx equal to 0. I mean, see, the point is very simple. Such a thing is quite obvious. Why? Because we are taking x belongs to a closure. I mean, this is the set A. So that means a closure is this part only, right? A closure is this part only, right? So x is actually very near to this point. So distance is 0, but we have to prove it mathematically, okay? So now again try to use the hints of the definition. Try to use the definition of superinfimum to figure this out, okay? Please take your time. Please let me know. So, Mustak, are you able to figure this out? Please try and let me know. Okay. So here the argument is as follows. Just hold a moment, please. Okay, so here the argument is as follows. So since x belongs to a closure, that means there exists a sequence n in A such that n goes to x. Okay, that means what? D of n comma x less than epsilon. So that means what? That dAx equal to 0. Okay, so that's what the argument is. So that means what does this tells that if x belongs to a closure, that means dx equal to 0. Okay, so what does that imply? That implies that is so corollary is if A is a closed subset of x, then dx equal to 0 if and only if x belongs to A. So that is an interesting corollary for this. Okay, so this is all about this distance function. Similarly, suppose we have a comma b sub of x. In that case, we can define dab. This can be defined with either we can say like infimum of dab, a belongs to a, b belongs to b, or it can also be defined as infimum of dab, b belongs to b. In either way, both are correct. Okay, so that's what this function is. So there are some problems as follows. Well, let me write the problem first. So first problem is as follows. Let A be subset of X be compact. Okay. Ooh, ooh. Okay. So A be compact subset of X. So the question now such that A intersection be empty. Show that DA comma B is greater than 0. So use the definitions what we have done till now and try to figure this out, that how to show that A intersection B is empty set. Okay, please take your time, think about it and let me know. Well, Mr. are able to figure this out by yourself, that whether how to show that DAB is greater than 0. Any guess or any idea? Okay, the argument is as follows. Okay, so the argument is contradict method of contradiction. So the solution is as follows. Okay, so assume DAB is equal to 0. Okay, that means by definition infimum, for each natural number n, there is an in A and Bn in B such that D of An, Bn less than 1 by n. Okay, so there is a first thing. Now A and B are given to be compact. A, B are compact. So that implies the sequence An and the sequence Bn has convergent subsequence. Okay, that implies what? That implies that there that Ank and Bnk be convergent subsequent. Suppose assume Ank goes to A and Bnk goes to B. Okay, so in this here we may put D of Ank comma B of Ank less than 1 by Nk, and the subsequent, so Nk is always greater than equal to N. So that implies what? 1 by Nk less than N. So that implies what? D, by putting limits, tending to infinity, we get D of AB equal to 0. So that implies A equal to B. So that implies what? A intersection B non-empty. But it's a contradiction to the given fact. So that implies D of A comma B is greater than 0. So this is the argument. So Mustaq, is the argument clear?
Yes.
Okay, thank you for confirmation. Okay, so the next problem is as follows. Mm, so let uh, let C subset of X be closed and K subset of X be compact such that C intersection K empty. show that dck is greater than 0. So the hint is that use equivalent conditions which we have seen in the starting of the session. So please try to do it by yourself. I shall get back to you in a few moments. Well, Mr. Are you able to figure this out? Okay. Like when hold a moment, please. Okay, so let me explain this argument. Just hold a moment. Okay, what happened? Ooh, screen share. Okay, okay. So, okay, okay. So here also we use the method of contradiction. Suppose dck is equal to 0. Okay, so that means what? There exists a sequence in C and a sequence can in K such that dCn comma Kn less than 1 by n. Okay. Now C is closed and K is compact. Okay. So since K is compact, so this sequence Kn has a convergent subsequence called is KNR. Okay. So that means what? D of CNR comma KNR less than 1 by NR. Okay. And assume that this KNR converges to little k. Okay. So by applying limit, what we are getting, this gives that limit of d of CNR comma k less than equal to 0. That means what? The sequence CNR converges to k as r tending to infinity. But k, but this belongs to in C and C is closed. Okay, that implies what? C intersection K must be non-empty, and that's what the contradiction is. Okay, so is the argument clear? Please let me know. So is the argument clear? Please let me know. Okay, I hope it is clear. So, well, so so here also the same process applied. We have used the criteria for compactness, that is any sequence is convergent subsequence. That's what the main tricky thing is. Okay, so there is nothing much to do to explain here. Okay, so the next problem is that, okay, the next problem is as follows. Just hold a moment. Okay, so the next question is a very interesting one. So let me write down the question first. The question is as follows. Let xd be a metric space and let f x to x be continuous function such that d of sorry d of f(x, f of y less than d of x, y for all x y with x not equal to y. Then show that there exists x naught in x such that f of x not equal to f of x. That means what? If a function and if this function is strictly contractible, then fx and x should be equal at some point. Okay, so please try to use prove this. So the hint is consider the function x going to d of x comma fx. Okay, so that's the hint. So please try to do it by yourself. Please take your time. So Mustaq, you are able to solve this. Please unmute yourself and let me know, or else otherwise please try. So are able to figure this out? Please let me know. So okay, Mr. are able to figure this out? Any case or any idea? Okay, so the argument is as follows. So consider this function x going to d of x comma x. Okay, so let gx equal to d of x comma x. We need to show that gx are not equal to 0 for some x naught. Okay, now uh, now now the point is that x compact, so that implies infimum of g, this thing has been attained. Okay, so basically we need to show that infimum of g equal to 0. Okay, so suppose infimum of g is equal to g of x naught. Now suppose gx naught is greater than 0. That means what? D of x naught comma f of x naught, that is greater than 0. Okay, now now by the property of this function f, d of x naught comma f of x naught, this is greater than what? This is greater than d of f of x naught comma f square x naught. This is greater than d of f square x naught, comma f cube x naught, dot dot dot. Okay. So now we have sequence of function f and x naught. Sorry, we have a sequence f and x naught. It has a convergence subsequence. Okay. So without loss of generality, let f on f a to the 1 in x naught is that convergence subsequence. Now since this is a convergence subsequence, so that means what? D of x naught comma f of x naught, this thing is greater than 0, and it's a contradiction. So thus g of x naught equal to 0 for some x naught. So that is the argument. Is the argument clear? Please let me know, Mr. Mustaq. Oh. Now the point is, okay, so that is the argument. Okay, So Mustaq, is the argument clear? Please let me know. Okay. Now the next question is as the following. The next question is that the next question is that let x comma d be compact metric space. Okay. And let f be onto such that d of fx xy is equal to d of xy. Show that, sorry, it's not, it is continuous function. Show that f is onto. Okay. So that, and okay, so Mr. Please think about it. Please let me know. So, or you have to assume that f is not onto. So in that case, some technique you need to use. Okay. Please think about it. Please let me know. Okay. Uh, Okay. So, Mustaq, are able to figure this out? That how to approach this problem? Any guess or any idea? So please try. Let me know. Uh, So the argument is as follows. Suppose assume f not on 2. So that means there exists x naught in x as that if of x not equal to x naught for all of x belongs to x. Okay. Now consider the function gx equal to d of f of x. So that is x naught does not belong to within the set f of x. Okay. Consider the set g of x equal to d of fx comma f of x naught. Okay. or maybe we can write, we can say d of f of x comma x naught. Okay, now this thing can be written as d of f square x comma f of x naught equal to d of f cube x comma and so on. Now f of x naught, we can assume this is convergent. So in this way, that means what? G of x equal to 0. Okay. But by definition, what are the g of x? G of x equal to d of f of x comma x not equal to 0. That implies what? X not equal to f of x. Correct? So that's what the argument is. These are same argument as the previous one. So both are exactly identical argument. So is it clear, Mr. Mustaq? Is the argument clear, Mr. Mustaq? Please let me know, or else we can move on to the next question. Okay. Okay. So now the next question is as follows. Okay, the next question is that. So next question is that. Just hold a moment. Let me find the question first. What is that? So the next question is as follows. Find two closures f1, f2 such that f1 intersection f2 equal to empty. However, d of f1 f2 equal to 0. Of course, it is this kind of example counterintuitive. Please think that. So hint is try to construct discrete sets. Okay, please think and let me know. Sorry, Karthik, there is some technical issue suddenly came, so that's where the problem occurs. Sorry, Karthik, for the inconvenience. Okay, so just hold a moment. Let me do things very proper. Well, oh wow. Okay, so okay, sorry for the inconvenience. Things are working fine now. Okay, so please try to find out two function two subs to close set is f1 f2, so the d of f1 f2 is 0. Okay, please take your time, think about it, let me know. Hmm. So please take your time, think about it, let me know. Hmm. Well, so the argument is as follows. Hmm. So choose f1 to be 1 by n with n belongs to n. Choose f2 to be 1 by n plus 1 by n, n belongs to n. Now show that d of f1 f2 is 0. Okay, please try to do it by yourself. So these are functions. For this one you need to show that d of f1 f2 equal to 0. Okay, take your time, let me know. So let's hold down one, please. Well, so see, hmm. Now the point is that now since the point, so the solution is as follows. See, the point is, if we choose any n belongs to n and epsilon greater than 0, then that means what, d of 1 by n naught plus 1 by n naught plus 1 by n, that is equal to 1 by n naught, that is the epsilon, correct? So What does that mean? That means that, that means that for any epsilon greater than 0, there exists f1 and f2 belongs to f1, f2 respectively, such that d of f1, f2 is less than epsilon. Which implies that d of f1, f2 has to be 0. So that is the argument. Okay, I hope it's clear. So that's the question. So that's what the question asks for. Now, so now we have the following question. Minus root 2 intersection q. Okay. The question is, show that minus root 2 comma root 2 intersection q is closed bounded subset of q is closed and bounded subset of q, but not compact. So how to do that? So minus root 2 is a closed bounded subset of q universal compact. So that means when you need to find an open cover which does not admit a finite subcover, right? That's what you need to prove. Okay. So how to approach this problem? Please let me know. Mustaq, please think and let me know. Well, so Pustak, any case or an idea how to approach this problem? So the argument is as follows. See, first of all, boundedness is okay, right? So we don't need to bother about boundedness. Boundedness is correct. There is nothing to bother about. Is it closed? That is the question. Because this minus root 2 plus root 2 intersection q, this is equal to root 2 comma minus root 2 intersection q. So that's why and this one is closed. Now the last part is not compact. Consider open cover un of minus root 2 comma plus 1 by n comma root 2 minus 1 by n. Okay. Clear this un covers minus root 2 plus root 2 intersection q. But it cannot have finite subchord. Why? Since otherwise, suppose un1 un give a finite subchord. In that case, union of un I is equal to 1 to k, that is equal to root 2 by plus 1 by capital M comma root 2 minus 1 by capital M. Okay. For yum, max of n1 n2 nk. Okay. So hmm. so so but there are points in between this. So that means what? That so root minus root 2 plus 1 by 2m does not belongs to this point. So that is the contradiction. Okay. I hope it's clear. So m is the max of n1 and nk, and we are considering all this root 1 by this. So that's why then we considered this all this unions, and that gives the answer. Okay. So that is the argument. So that tells that although what So that tells that all in metric space, that tells that Honey-Buller theorem is true in R to the power n, not in R. So that's what the thing this exercise is telling. Okay. Now show that okay. Now the next question is that is the set x, y, z in R3, so that x square plus y square minus z square minus 1 compact. Is this thing compact? Yes or no? So that's what you need to figure out. Please think about it and let me know. Take your time. Any idea, any guess, Mr. Mustaq? Please let me know. Any idea, any guess? So see, first of all, how this thing. So this is what? This is two-sheeted hyperboloid. Well, just hold on a minute. Let me check. Well, it is a two-sheeted hyperbola. So that means diagrammatically it looks like as follows. Okay, so both infinite. So of course it is not bounded. So that is this thing is not bounded. Hence, not compact. Okay, that's what the argument is. Since it's not bounded, so it is not compact. Now next show that the orthogonal matrices show that the group of orthogonal matrices are compact. So how to show this or how to prove this? Any so Musta, please try. So so see, first of all, Mustaq, any guess or any idea? Please let me know. See, the point is that for a for a matrix with ON, look at the columns, okay? C1, C2, C3 dot dot dot. Now, the point is norm of Ci that is equal to 1. That is C1 squared dot dot, C1 on square dot C1 square that is equal to 1, okay? So that means what? All Cii are bounded. This is the one things. And the relation AA transpose equal to identity, it is a closed relation. So that means what? This the set On is compact. We can think On as a sub of r to the power n square by 2. So, so in this way, On is a compact subset of R. So that is the argument. Is it clear, Mr. Mustaq? Please let me know. Okay. The next problem So okay, so next problem is that is GLNR compact? Sorry, hold a moment, let me write it down. Is GLNR compact? Please think and let me know. That means you need to check two things. That whether it's closed or not, or bounded or not, right? These are two things you need to figure out. Please take your time, think about it, let me know. It shouldn't be very difficult. Okay. See, GLNR means what? That is, determinant A is non-zero, right? But the point is, set of all matrix such as determinant A is 0. It is a closed set. So that means what? GLNR is open and ANR. So that means GLNR is not compact. So that's what the argument is. Okay. I hope that this much is clear. Okay. So that's all for today. We shall meet on the next Sunday. So I am leaving the session. Thank you.